Next chapter is optical prescriptions and spectacle lenses. So the lenses which we discussed in the previous chapters, they have many uses in ophthalmology. Lenses are used as optical aids for patients with refractive errors and in the form of spectacles or contact lenses. Also as a low vision aids, which we will discuss in next chapters. Lenses are also an essential component of most of the instruments used in ophthalmology, which we will discuss in the next chapters. In this chapter, we will discuss the use of lenses in spectacles only. So, when prescribing a spectacle lens, the properties of lens required are specified in a certain way, which we will discuss. The writing of spherical lens and cylindrical lens is different from each other. In case of spherical lens, it is only written alone. The number is written alone, like for example +2 diopter spherical. DS means diopter spherical, or -3 diopter spherical. This is this way we write spherical lens. While in case of cylindrical lenses, we should write the diopter power as well as the axis. For example, +1 DC is the dioptric power and the axis is 90 degree. So this is the way how the cylindrical lens is written. The axis of cylindrical lens is marked on each trial lens by a line, is shown here. And these trial frames are marked according to a standard international convention. So suppose this is +1 diopter lens and it is placed with its axis vertical, so it will be written as +1 DC with axis 90 degree. So DC means diopter cylinder. Diopter DS mean diopter spherical and DC mean diopter cylinder. Sometimes the patient need both spherical and cylindrical correction. So this is known as toric astigmatic correction. So it will be written, then both are written, first the spherical and then the cylindrical with axis. So in these cases the cylindrical lens is usually placed in the front of the spherical lens to allow the axis line to be. Next topic is transposition of lenses. During transposition, the lens prescription is changed from one lens form to another lens form, and both are optically equivalent forms. So this process is known as transposition of lenses. Transposition of lenses, there is simple transposition of spheres and simple transposition of cylinders, and then there is toric transposition. So there are three types of transposition. In simple transposition of spheres, so this applies to the alteration of the lens form of spherical lenses. The lens power is given by the algebraic sum of the surface powers. Suppose all these are the +3 diopter spherical lenses, and they can be written in all these forms, and all these forms are will be equal to +3 diopters if we add them algebraically. Next is simple transposition of cylinders. So in this we change the description of toric astigmatic lens. The cylinder is expressed in the opposite power. So during transposition of cylinder, the power of cylinder is changed from positive to negative or from negative to positive. Simple transposition of the cylinder is often necessary when the examiner wishes to compare the present refraction with a previous refraction. So it is a change in the prescription and the cylinder is expressed in the opposite sign. There are 3 steps. The first step is the algebraic addition of sphere and cylinder. In this example, plus 4 sphere and plus 1.5 cylinder, they are both added, which will give us plus 5.5 diopter sphere. It is the new power of the sphere. So this is the first step, to add sphere and cylinder. The next step is to change the sign of cylinder. So change the sign of cylinder from 1.5 to minus 1.5, and the numerical power is retained. Both are 1.5. Third is rotate axis of cylinder through 90. So 180 is rotated, which gives us 90 is rotated, which gives us 180. In the second example, 170 is rotated by 90, which gives us 80. Detection of lens type. It is possible in clinical practice, it is necessary for practitioner to identify the type and power of the patient existing spectacle. So detection of lens type. Now it is possible to determine whether a given lens is spherical or astigmatic or a prism by studying the image formed when the two lines, as you can see, crossed at 90 degree are viewed through the lens. So spherical lenses cause no distortion of this cross. However, when the lens is moved from side to side or up to down along the arms of the cross also appears to move. In case of convex lens, the cross appears to move in the opposite direction to the lens. So the lens is moved upward, the cross moves downward. In case of plus lenses, the movement is opposite. The lens movement and the cross movement is opposite. In case of plus lenses, there is against movement. While a movement in the same direction is the lens, with movement is observed in case of concave lenses. In case of minus lenses, there is with movement. In case of the astigmatic lenses cause distortion of the cross unless their axes coincide with these cross lines. Rotation of the lens thus causes a scissor movement, as the cross lines are progressively displaced. Rotation of a spherical lens has no effect upon the image of cross lines. So rotation of the lens causes a scissor movement as the crosses are progressively displaced. So first we identify the principal meridians of astigmatic lens and they are aligned with the cross, and then each meridian is examined as that for spherical lens. Now how to find the optical center of a lens? It is found by moving the lens until one cross line is undisplaced. Then a line is drawn on the lens surface and superimposed on the undisplaced cross line. This process is then repeated for the cross line at 90 degree. Then the point where both lines drawn on the lens intersect is the optical center. Now detection of prism. As you know that a prism has no optical center, and the prism will displace one line of the cross regardless of its position. So as you know, this line has been displaced regardless of the position. Furthermore, the direction of displacement is constant. Now, this test is most effective if the cross lines are placed at the furthest convenient distance and the lens held well away from the eye. Now, neutralization of power. The power of a lens can also be found using the technique we already discussed. How? So first of all, the nature of the unknown lens is determined. Then lenses of the opposite type and known power are superimposed upon the unknown lens until a combination is found which gives no movement of the images of the cross lines when the test is performed. Now at this moment, two lenses are said to neutralize each other. Then the dioptric power of the unknown lens must equal that of the trial lens of opposite signs. For example, a +2 diopter lens neutralizes a -2 diopter lens. Now in case of astigmatic lenses, each meridian must be neutralized separately. Spectacle lenses are named by their back vortex power. To neutralize accurately, the neutralizing lens must be placed in contact with the back surface of the spectacle lens. However, with many highly curved lenses, this is not possible and an airspace intervenes. So it is then better to place the neutralizing lens against the front surface of the spectacle lens. Neutralization is somewhat inaccurate for curved lenses of more than about 2 diopter power, and an error up to 0.5 diopter may be incurred with the powerful lens. The Geneva lens measure. So the Geneva lens measure can be used to find the surface power of a lens. To find the surface power of the lens by measuring the surface curvature, we can find the surface power, and then the total power of thin lens equal the sum of these surface powers. This instrument is calibrated for lenses made of crown glass only. The refractive index is 1.523, so a correction factor must be applied in case of lenses made of materials of different refractive indexes. The Fusimeter or lensometer or vertometer. Fusimeter is used to measure the vortex power of a lens. Also the axis up in astigmatic lenses and the measure powers up in astigmatic lenses, and also the power of a prism. The power of a lens, the axis of an astigmatic lens, the measure power of astigmatic lens, and the power of a prisms. It consists of two parts: a focusing system and an observation system. The focusing system and an observation system. So a focusing system and an observation system. The focusing system comprise of movable illuminated target. This is a movable illuminated target, and a fixed collimating lens. This is a fixed collimating lens. The target is in the form of a ring of dots or crossing lights. As you can see, these are crossing lines and there is a ring of dots. This is usually the target, behind which there is a green light source to eliminate chromatic aberration. Now this collimating lens, this is the collimating lens. This renders light parallel when the target is located at its first principal focus. So light emerging from the focusing system is viewed through this observation system. So next we have observation system, which consists of telescope with eyepiece adjustable and reticule. So before use, the instrument should be set at 0, the eyepiece adjusted until the dots and the reticule, they are sharply focused, so it should be sit at this 0. So the Fusimeter measures the vortex power of the lens surface in contact with the lens rest. So to examine the spectacle lens, which are designed by their back vortex power, so mount the glass with the back surface of the lens against the rest. While examining the bifocal lens, so as well as measuring the back vortex power of the distance portion, it is necessary to measure the aid for near. So the distance and near both should be measured. So the front vortex power of both the distance and near portion should be measured, and the difference being the bifocal aid. So the target is moved until light entering the observation telescope is parallel. How will we know that it is parallel? A focus image of the target is seen by the observer. The distance through which the target is moved is directly related to the diopter power of the lens under test. So this will be the diopter power. The instrument is so calibrated that the power of the lens can be read off in diopter. When a spherical lens is tested, the images of the target is seen as a ring of dots. While in case of astigmatic lenses, the target must be focused separately for the two principal meridians. When an astigmatic lens is tested, the image of the target is seen as lines. As you can see, these are the lines. The length of the lines being proportional to the difference between the two principal powers, that is the cylindrical power of the lens under test. To examine an astigmatic lens on the Fusimeter, the lens shown in this figure, the instrument is adjusted until one set of line foci, these are line foci, is in focus, and the reading is +1. +1 is recorded. The instrument is further adjusted until the second set, this is the second set of line foci, they come into focus, and the reading is +3. The axis is 180. The axis of the lines is 180 as it is recorded. The reading, first reading gives the spherical power. The cylindrical power is calculated by the algebraic subtraction of the first reading from the second. So 3 minus 1, it will give +2. +2 is the cylindrical power. The axis of the cylinder correspond to the axis of the second reading, this reading axis. So it is 180 in this case. So the result is +1 diopter spherical, +2 diopter cylindrical, axis is 180. Now if there is prism incorporated in the lens, the image of the target will be displaced from the center of the eyepiece reticule. The cross lines of the reticule are calibrated in the intervals of one prism diopter, so enable the prism power to be determined. So the image is seen displaced toward the base of the prism, because the image of the target is inverted by the eyepiece telescope, so it is displaced toward the base. In order to detect the prismatic effect of a lens which has been decentered, this formula is used: F multiplied D. P is the prism power in prism diopter, F is the power, lens power in diopter, and D is the decentration in centimeter. So this is lensometer cross-sectional view. So this is the eyepiece, this is reticle, and so we have then the objective lens, then we have the telescope, this is telescope, then we have the lens stop, this is the unknown lens which we are going to measure, this is collimator objective, this is reticle, and this is light source, This is collimator and this is power dial from plus 20 to minus 20. Automated phosimeter depends on the principle that the degree to which the beam of light is deflected as it passes through a lens depends on the focal and prismatic power of the lens and the distance from its optical center. In automated phosimeter, a square pattern of 4 parallel beams of light is passed through the lens to be tested. The deflected beams strike a photosensitive surface which measures the deviation of each of the beams from its original path to compute the lens measurement. Tinted lenses. Tints are either absorptive, like chromium and magnesium, silica, or reflective. What is the purpose of tinted lenses? It may be to screen out unwanted or harmful radiation. For example, laser protective goggles or cosmetic. Unequal absorption of different wavelengths produce a colored tint. For example, a yellow tinted filter absorbs all wavelengths of light except those in the yellow part of the spectrum, which it transmits. So a tinted lens modifies the spectral profile of the radiation passing through it. The performance of a tinted lens is described by a transmittance curve, which plots the percentage transmission of incident light for each wavelength. This is the wavelength and this is the percentage transmission. A neutral density filter absorbs all wavelengths to the same degree and does not alter the spectral composition of light. Tints may be of fixed color or photochromic, in which transmission characteristics vary with the intensity of incident light. A tint may be added to a lens by permeation by means of a coating or as a solid tint. Most plastic lenses are tinted by immersion in a dye, which permeates the lens to a uniform depth to produce an even tint. Darker tints are produced by prolonged immersion. A solid tint is incorporated evenly throughout the lens and absorption of radiation is therefore greater where the lens is thicker. Filters. Ultraviolet filter. Ultraviolet light comprises approximately 5% of the total solar radiation. Ozone in the Earth's atmosphere absorbs almost all solar ultraviolet C radiation. Ultraviolet which strikes the Earth's surface, approximately 10%, is ultraviolet B and 90% is ultraviolet A. Ultraviolet light exposure may also come from arc welding and ultraviolet emitting light bulbs. CR39 lenses absorb ultraviolet light shorter than 370 nanometer. Infrared filter. Infrared wavelength near 1400 nanometer are very hazardous. Filters for these wavelengths are usually incorporated into protective goggles and face masks. Heat absorbing filters. They act as infrared filters. They maximize the transmission of visible light. Blue light filter. They vary in tint between yellow and red. They increase contrast and facilitate distinction of light in dark areas. They are used by mountaineers and skiers. Photochromic lenses. Photochromic lens change its transmission characteristics depend upon the intensity of incident radiation. The lens becomes darker in bright light. The process of darkening is more rapid than that of lightening. The reaction in glass and plastic are different. Glass photochromic lenses comprise colorless silver halide crystals suspended in borosilicate. Electromagnetic energy dissociates the silver and halogen and it causes darkening. So electromagnetic energy dissociates this silver and halogen, and that's why darkening occurs. in glass photochromic lenses. Each type of glass has an optimum activating, usually ultraviolet or blue, and bleaching wavelength. The tint will depend upon which wavelength predominate. Heat opposes the effect of light. Thus, glass darkens more easily when cold and lightens more easily when warm. A glass lens becomes gradually darker over time if it is used repeatedly. A number of organic photochromic compounds are used to coat or impregnate plastic lenses. They are more wavelength specific and undergo structural transformation when stimulated. Fatigability of the material over time reduces the darkening which occurs. The time delay in the reaction of photochromic lenses make them unsuitable for use where lighting conditions change rapidly, for example when driving through tunnels. So the time delay in the reaction of photochromic lenses make them unsuitable for use where lighting conditions change rapidly. Anti-reflective coatings. The reflection of light from the surface of a lens may be reduced by coating it with a material the thickness of which is quarter of the wavelength of the incident light. These are lenses without anti-reflective coating and lenses with anti-reflection coating. So this is half of wavelength thickness. Thickness is half, a quarter of the wavelength of the incident light, and this is the lens. Lens without anti-reflection coating, and here it is anti-reflection coating. So this is incident light, this is 98% light is transmitted and 2%, less than 2% is reflected. And when there is no coating, 90% is transmitted and 10% is reflected light. Light rays which are reflected from the surface of lens travel a distance of 1/2 of a wavelength further than those which are reflected from the surface of the anti-reflective coating. So then destructive interference occurs, which reduces the reflection of light. In contrast, coating which has a thickness half the wavelength of the incident light produce a mirror coating because of constructive interference. Any wavelength may be selectively reflected by a coating which is half of the wavelength thick. Mirror coating are usually combined with an absorptive tint.